Hello, everybody. I'm Swaroop.
Hey, everyone. I'm Dhaval.
And we want to start with a story about forecasting. So we work at a company called DoorDash. If you haven't heard of us or used our service recently, we are a local commerce company connecting the local merchant to the local customer via the local dasher who does the delivery. So why is forecasting important in our context? As you can imagine, because real people are involved here, balancing supply and demand is crucial. So if you are expecting more orders this weekend, then we need to make sure we have enough dashers who can deliver those orders on our behalf. And so we need to make sure they are recruited ahead of time. These are not AWS instances which we can bring up and down any moment, right? Similarly, if we are expecting more orders next weekend, you can kind of imagine that we would have more customer support tickets, which means we would need to have more customer support agents, which means we would need to tell our vendors, hey, we need more folks managing our, answering our customer support tickets. So these are the reasons why forecasting is critical to us at DoorDash. Now, take the case of the ATS algorithm, that one of the algorithms that we use. When there is a single time series, there's just only so much data. So you cannot iterate on data, so what do? You need to use a grid search to find the best model that works for the given data range that we have. So the code was parallelized using joblib and distributed across machines using joblib Spark. And it worked fine in terms of accuracy, but we had some challenges. Most importantly was scale. Given the grid search that we were doing, we could expect on one of our larger forecasts, we could expect like 1.6 million model trainings. Now that's a lot of model training that is happening, and it was parallelized using Spark, and the cost was super high given the value that we get from it. The jobs would run for several hours, it would break, have random error messages, so it was kind of a issue, and that's when me and a couple of others from the machine learning platform team got involved. So my question was, like, why is this so slow? Like, I don't understand why, if it is so parallelizable, why is this running slow? And how can I inspect or debug what happened? And that's when I heard about Ray. And I was like, oh, this Ray dashboard looks really cool. Can I make use of this to understand what's happening inside? In our team, we have something called a Yak Day, which is kind of like a hack day, where we take one day in a month to either pick up a backlog task or learn about something that you've been wanting to learn. So I took the Yak Day opportunity to learn about Ray. And it was a very simple hack. I just took the joblib lines and replaced that with a ray.remote, right? And just literally, this is the actual diff. This is not a made-up example. This is the actual diff, right? And it was running on my laptop. The things that I loved was it was simplicity. For a data scientist or a machine learning engineer, they don't have to think, oh, is this running on my machine? Is this running on several machines? Which was the problem with the earlier code that we have. You just use ray.remote, and the Ray cluster knows where to send it off to. And the debugging and monitoring was great. I could go down to a specific task and see the logs specifically for that, which was a far better experience than looking up a log file of everything jammed in one log file. And it was actually faster too, which was surprising. So then we decided to actually benchmark this. Like, running on the laptop is fine, but how does it actually mean if you do a proper benchmarking? And to our surprise, it was 35 to 45% faster and 45 to 55% cheaper. And that was really exciting for us. So we took a decision that, hey, we want to double down on Ray for forecasting. And that was when the story switches to distributed training.
Thanks, Swaroop. So let me first explain why we train machine learning models at DoorDash. Like, we have a variety of use cases. And let me do that in the context of an order delivery process. So first, we have the step of creating your order. So this is where you are browsing through the DoorDash homepage. And our search, ranking, and recommendation models, they play a huge role here. Next step is the order checkout. So this is where the ETA models, that is expected time of arrival, they try to estimate when you will receive your order.
And one of the most challenging things is an ETA model is actually not that simple, because not only do you have to take historically how long has this restaurant taken to prepare a dish, but you also need to know how are they backlogged in real time, are they slower than usual, or are they faster than usual? So the ETA model is actually not as simple as it sounds.
Yes, and after that, like, we also have certain fraud detection models, because when you're actually making the payment, we need to identify fraudulent transactions and flag them as needed. Next is dispatching the order. So this is where our logistics team leverages several ML models. Like Swaroop mentioned, they compute like how much time the restaurant will take to prepare the order, how much time will the dasher take to arrive at the restaurant and arrive at your place to deliver the order.
Yeah, and another example of complexity there is you don't want to send the dasher too ahead of time, because if you send them 10 minutes before to the restaurant, they're just standing there and waiting. The restaurant doesn't like it, the dasher doesn't like it. But you have to dispatch them at the right time. And at the same time, at the right time when the order is ready for pickup, not when we estimated it to be ready, right? So if the restaurant we detect is actually slower than usual, we need to dispatch the dasher later than usual. And in which case, the dasher might even change based on the expected time of dispatch, right? So you might pick up different person to go farther and a different person to go nearer, depending on when is the expected time of the order to be ready.
Yeah, and there are like several factors like traffic or weather conditions, and which are like out of our control. So we need to take into account all of that as well. And the final step is delivering your order. So this is where we leverage ML models to identify like what channels we should invest in to acquire more and more dashers on our platform, and what's the right time to mobilize them. And we also use like image recognition deep learning models to identify if the order was delivered correctly. And this was particularly helpful during COVID times when the interaction between the customer and the dasher was limited. So in the last 1.5 years or 2, if you are about to pick up your DoorDash order and you see your dasher clicking a picture of it, this is why. So like I said, we have several use cases at DoorDash that we train ML models for. But we have traditionally used tree-based or simple PyTorch models for, okay. We have used like tree-based or simple PyTorch models for most of these use cases. But what we were noticing now is that there was an increasing number of deep learning use cases at DoorDash. Like users wanted to train larger models on larger data sets in less time. So we did develop a framework for distributed GPU training using Databricks, Horowat, and Petastorm. This was an extremely painful process. It took us weeks, and Cornell in the audience can vouch for this. It took us weeks to set this up for just one model training script. And even though the results were encouraging, this was not easily generalized across all the use cases. And on the other hand, Ray provided easy-to-use APIs with solid documentation. So this is one reason why we decided to conduct a POC of sorts on Ray in Q4 2022. So before we dived into the POC, we also ran some benchmarking experiments like forecasting team did. And the idea here was to benchmark several model training frameworks, mainly on 2 pillars, cost and velocity. So as you can see, we benchmarked Ray datasets with Horowat and Petastorm as well. And you can see that we saw a 46% reduction in training time for 2 epochs. And as far as cost is concerned, we saw a 42% reduction when we were hosting these applications on Kubernetes rather than on Databricks. Okay, I'll let Swaroop talk about the next chapter in our story.
So funnily enough, around this time is when we attended Ray Summit last year. And it's funny that we are actually on stage this year. So one of the things that we learned at the first Ray Summit last year was before, our training and serving required a lot of integration. Like you want to add a new library, okay, we have to actually integrate it into our serving or training stack. Now with Ray, all of that came built in for free, at least the most popular libraries. So we didn't have to reinvent that. So that single point of integration was very attractive for us. And this was actually some of the notes that we shared with the team. And this is actually a screenshot from the takeaways section. 2 things resonated for us. One is the Spark for data, Ray for compute idea. That seemed to be my takeaway from all the Ray Summit talks last year. So the question I posed to the team was, just like Kubernetes standardized compute infra, can Ray standardized ML compute infra? That was kind of the question we had at that time. And that's when the team decided to take a bet on Ray, and that's when Project Lucent is born.
So yeah, coupled with all the interesting and encouraging benchmarking results that we just showed and all the learnings from the Ray Summit as well, the ML platform team decided to make a bet on Ray for our next generation of training and inference frameworks. And Lucent is the training framework that's built on top of Ray at DoorDash. So initially, we had two different frameworks for forecasting and training. So with Lucent, we took the opportunity to unify them under one common training platform.
Yeah, the reality is I was just looking for an excuse to work with Double.
Yeah, because we thought forecasting is just another type of model training, so why have our users onboard to two different services? And this greatly helped us reduce duplication of effort, code, and speed up the velocity, development velocity. So Lucent is built on top of Ray and Daxter. While Ray is the compute backend, Daxter is our orchestration engine. And it enables us to implement several things like continuous training, which could be schedule-based, or if the upstream data becomes available, how do I automatically trigger my training job, dynamic creation and tearing down of clusters, and all of those nice things. So now I will go through some of the challenges that we encountered during our POC process. And these are long 3 slides, so please bear with me here. First was, of course, understanding Ray. This was a completely new technology for most of us. So we had to understand its concepts, the APIs, and all the bells and whistles that it came with, right? But the Anyscale team has been of great help here. They are super responsive in answering all of our questions and even jumping on Zoom calls if and when required. So huge shout out to them here. Next was several infrastructure challenges. So we were setting up Ray on the existing Kubernetes setup at DoorDash. And the Kubernetes clusters at DoorDash were not designed for these type of workloads. They are technically designed to host microservices at the company. So we needed a lot of help from several infra teams at DoorDash. We had to make sure the clusters got created with the right permissions to access all of our internal resources and libraries. Next was the dynamic cluster creation. So idle clusters lying around simply incur a lot of cost. And we noticed it would also block other clusters from getting created when limited resources were available. So we had to identify how do we dynamically create clusters when needed and tear them down once the job has completed. So we also looked at Ray's auto-scaling here. So one thing we would do is we would set the min worker count to 0. So whenever the job is not running, the workers would scale down. But there was a trade-off here, because next time whenever the users would start a new job, they would have to wait for these worker nodes to come up again. So we had to deal with all of these trade-offs and find a sweet spot there. Next, and I would say the biggest challenge we faced was providing stable GPU support to our customers. And some of the challenges here were we were noticing that the containers would lose access to GPUs after a random amount of time. There were several incompatibilities between the CUDA and the NVIDIA driver versions. And on top of that, we were experimenting with several instance and GPU types. So the NVIDIA team here was of great help. They would try to explain why something is happening or what is happening and unblock us wherever possible. And the infra teams and the MLP also joined hands here and made sure that Lucent reaches a stage where we can claim that our users have stable GPU support on the Ray clusters. But after doing that, the next challenge was GPU availability. As we all know, there's a shortage of GPUs in the industry. So this made us carefully estimate how many GPUs we would be needing in the near future. And it helped us secure some dedicated instances, which has proven really, really helpful to unlock some critical model training use cases at DoorDash. This is the final one, I promise. So we also had certain unforeseen customer requests. We were so focused on building the infrastructure, on making sure that all the pieces align, we forgot that our customers might need something totally different, right? So one common ask there was, how can we get more observability into our training jobs? So for that, we had to build support for PyTorch Profiler and TensorBoard. We'll be going over these in the later slides. And the next one was sometimes the underlying instance on which we are hosting Ray clusters would be scheduled for maintenance, or the node might restart because of disk pressure. And this would lead to our users losing all of their files that they had stored on the Ray clusters. So this was a very critical ask, and we had to implement support for persistent volume to make sure this doesn't happen again. And we also started exporting pod logs. So whenever there would be a node restart, we could look at the logs to identify what went wrong. And last but not the least, we completely did not estimate the huge support overhead that came with this. As I said, understanding Ray was a big challenge for us. But it was an even bigger challenge to educate our customers about Ray. So there were so many questions, so many doubts, and there are so many nuances to Ray that each and every question required like a different type of investigation on our part. OK, we are done with the challenges. Now, what did we build with Lucent? So at a high level, we built 2 different workflows for development and production. And these are like some important differences between the two. So the dev workflow was intended to provide our users with a notebooking environment for faster iteration so they can try out different model architectures really quickly. But once they are happy with their model architecture or the training script, they need to commit this code to a centralized GitHub repository. This way, we ensure reproducibility, and we also make sure that every model in production has gone through code reviews. Surprisingly, these 2 things were really, really important to our customers.
Yeah, if you ever had the challenge, like, where's the training script for this model, then this is how we solved for it.
Yeah. Fun story, we were actually looking at implementing direct deployment from the dev environment itself, but our customers were the ones who said, no, we are fine with lesser development velocity, but we do want our code to be checked in. So that was a fun learning there. OK, so let's do a quick walkthrough of these 2 environments. So this is our code repository. So basically, they clone this repo, and they create a new project directory within it. As you can see, we have a project directory here called Ray Summit Demo. This directory must have the job config YAML that you see here. And this job config file is where the users can define exactly what resources they want. For example, here we are creating a Ray cluster with 4 worker nodes, actually 2 worker nodes with 4 GPUs on each. And it can also contain a list of all the libraries that they want us to install on their clusters, and some metadata like Slack IDs for notifications and timely updates. Once the project directory is ready, they need to run this one command, which will create the Ray cluster for them as per the job spec that I just showed you. And it will also transfer all the files in their project directory to the remote Ray cluster. Now, in the end, they just need to visit this URL that you see in the end to get to the notebooking environment. So this is the Ray dashboard. As you can see, the cluster is created, 2 worker nodes with 4 GPUs on each. And this is the notebooking environment that I was talking about. So on the left, if you see, the Ray Summit Demo project directory has been copied over for them. On top of that, we also provide a simple starter onboarding notebook for them. They only need to update the command and the working directory to kickstart a new Ray job. So we have this Lucent library that tries to abstract away a lot of boilerplate Ray code for them. So just by running the submit command, they would have kickstarted a Ray job. And in response, they get certain URLs, like where is the job running, what are the metrics, and the TensorBoard and PyTorch profiler pages as well. So as you can see, this is the TensorBoard page for the job that got started. This is the Ray cluster metrics page. So we don't want them navigating through these different pages. We are providing them the required URLs then and there. Over here, they can have a look at certain metrics like what's the GPU usage like, or what's the disk pressure, and things like that. And finally, when they are done experimenting on the notebooking environment, they will merge that code in. And the CD process will handle creating a new Daxter job for them. Now, now they can come to the Dagit UI play with the job config here and use the command line arguments to run the same job multiple times with different parameters if needed. So as you can see here, all of these 3 jobs were kickstarted at the same time, just with different parameters. So essentially, you could kickstart a Llama 7B, 13B, 70B fine-tuning job at the same time, once you know what the architecture and the data is. So along with leveraging Ray for model training, we also built our next generation of inference platform on top of it, and that is called ARGIL. Now, I'm not going to go into much details here because Sid and Cornell from DoorDash are presenting exactly this tomorrow. But at a high level, ARGIL is focused on extensibility, flexibility, and GPU inference. So do attend their talk tomorrow if you are interested to learn more. And I hand it back to Swaroop.
Yeah, and so this is what Project Lucent was. So how did we benefit from it, right? And I would say the bet paid off because, as I'm sure you were aware from the keynote today, LLMs happened. Now the question was, how do we support it, right? It took us all by surprise, but folks were interested in fine-tuning open source models like Falcon, and now, as of the last few months, it's Llama. So how do we support that? And the challenges was that there were things like data parallelism, model parallelism, multiple GPU support, all of these things that we needed to figure out. And luckily for us, the Anyscale team was providing support for this on top of Ray. And that's how we were able to support LLMs fast. Now, in the process, we had to figure out what is an A10, what is A100, what is H100, what is V100. I'm sure many of you have learned these in the past year along with us as well. My takeaway is that if you had not bet on Ray, we would have easily lost 6 months in trying to figure out our LLM story. And because we already had a Ray training and Ray serving in place, and Anyscale kept adding LLM support, we were able to move fast on LLMs. So what do we use Lucent for? We have training DNNs, deep neural networks, data parallelism via Ray data sets, model parallelism via deep speed. All of these things, again, was possible because of the single point of integration, which is Ray. Fine-tuning LLMs and GPU training. So these are all the new functionality that we added in the past 1 year thanks to building on top of Ray. So what's next? As you noticed the GPU stability challenges that we had, one of the things was we wanted to, one of the advice that we got from NVIDIA was to switch to their GPU operator. And we had some other challenges as well, because of which our compute team decided that migrating to AWS Elastic Kubernetes was a better path. So we have just started on that journey. Getting started for machine learning engineers need to be much faster. So we are thinking of adding templates. So hey, you want to do a Llama training template? Here you go. Like here's your template. You can just punch in your data and get started. All right. Easy saving and loading of checkpoints. A lot of times we get the request from saying, hey, I want to save this checkpoint and continue training epochs later. How do I do that? Right now, it's a manual process, and we are hoping to streamline that. And who here hasn't faced dependency hell in Python? One of the major problems in stability for our MLEs is like, hey, it's just not working. What's this magic combination of library versions that works? And we're trying to figure out a story there, hopefully have some standard package combinations available and ready for our MLEs to use, and so that they don't have to figure this out on their own. And one of the interesting challenges we faced recently was the node, the GPU runs out of memory, and the node dies, and all that the user sees is actor died because node died, and they're like, oh, Ray is not working. And when we dig into the logs, it's like, oh, actually you ran out of memory, or you ran out of disk. So we want to preempt that discussion by proactively sending Slack alerts to the users saying, hey, your cluster is running out of memory or running out of GPU. And I've often also seen the case where they use 4 out of the 8 available GPUs on that single machine and then run out of GPU memory, right? Like, oh, no, use all the 8 GPUs, right? And similarly, the dev clusters are running all the time now. So we are depending on good faith of MLEs to shut down when they're not using it. So obviously, that's not a long-term solution. So we want to introduce idle shutdown as well. So yeah, with that, closing thoughts. Velocity and efficiency are evergreen. we were looking at dev velocity, and that's why we started looking at Ray. And it turns out we got efficiency as well by Ray reducing costs for us. So because of velocity and efficiency were our focus, it was an easy sell within our platform team. Bet on open source projects like Ray. All of us are here because Ray is open source. Some of the do's and don'ts is have sample benchmarks for MLEs. They are always constantly asking us, hey, how much have you benchmarked this for? Can I train 1 billion data points, right? And they expect answers to these questions, which we are working towards. Have sample projects like the cookie cutter templates. Anyscale office hours was very helpful because we are not the experts on Ray, Anyscale is, so getting them in and getting them directly to answer questions was super helpful. Some don'ts. Don't assume MLEs understand Ray. They understand PyTorch, they understand ML, but they do not understand Ray. And bridging the gap is something that we are working towards. Don't position Ray as a replacement for PyTorch. It's just different part of the stack. Ray is at a much lower level in the stack than PyTorch or CUDA issues. So there are different parts of the stack. Often we ran into the issue where folks thought the Ray should have solved the CUDA issues, which is not at all the case because there are different parts of the stack. So with that, yeah, we are hiring. So if folks are interested in working on things like these, please let us know. And we have 3.5 minutes left, so if there are any questions, we'd love to take them. Yeah, hi.
Hi. So I have 2 questions. The first is you mentioned that you have Anyscale office hours. Like, how does that work? Like, do you?
It's a support contract with them. So
do you use managed Ray by Anyscale?
No, we do not. We are running in-house as of now. Managed Anyscale hosting is an option for us in the future. But right now we are running Ray in-house using the KubeRay operator. But Anyscale office hours is more for answering questions. If MLEs have questions about how do I do this, how do I checkpoint in Ray, we may not be the experts on that, so we have folks from Anyscale coming in and answering questions.
Got it. That's awesome. So it's only for support.
Yes.
Okay, that's awesome.
Correct.
The second question I have is for Project Lucent and upcoming projects. Like, how big is the team behind it?
So Lucent itself was built by, I would say, 2.5 engineers, depending on how long you count someone's contributions. So yeah, 2.5 engineers over the past year is what I would say.
Got it. Thank you so much.
Yeah. Yeah.
So you mentioned that for last year's takeaway, you use Spark for the data processing and use Array for the training and inference. So for today, are you still using the Spark for the data pre-processing, or you plan to use Array data for pre-processing part?
Great question. So are we still using Spark or are we using Array data, right? Our experience has been, and we have benchmarked and prototyped Dask and what's the other one? Modin. Along with Ray. The truth is those projects are still early. They are useful if you're already on Ray. But since we already have a Spark setup, Spark is like just way ahead right now. I still think Spark for data, Ray for compute is the best way to go for now. Where Ray data is super helpful is for loading that data for training, right? And Ray data is still the best option there. Yeah.
And how do you resolve currently the transition between Spark data and then use Ray?
So we have a DoorDash data lake that acts as the gateway across. So we have a blog post on this called on DoorDash. It's a system called Fabricator. So our MLEs come in, write Fabricator code, check in their script, and again, we use Daxter to run the data generation on a daily, hourly, whenever they need it. And it writes to the data lake. And you can use the same Fabricator APIs in the training to load back the same data for training. And again, we are using Ray data to read that in, but it's written in a standardized like Parquet, the standard data lake stuff, and then read back with easy to use APIs that we have provided internally. Does that answer your question?
Yeah, so any like a benchmark you guys had done or any performance bottlenecks?
Sorry?
Any benchmark you guys had done by like, using the reading and write out data?
Reading and writing benchmarking. Are you talking about the data lake or Ray data?
Yeah, about the data lake, because, your using Spark, and then use Spark to output the data, then use Ray to read in the data.
Right,
So
right.
those are like an extra step, and also just curious about what's like a performance look like while you're doing this.
I'm not sure if I've done any benchmarks.
Yeah, I don't think we have done benchmarking for this. They are two totally different services. Like even the data that's written on data lake, it's not just being consumed for model training.
I know we did a benchmark to decide on the format, like are we going with Iceberg, or are we going with Parquet, or with something else. I believe there were a whole host of considerations, and our data platform tech steering group decided on, what was it, Delta as our final format. So I believe there was benchmarking for that, but not the Ray data
Reading
side
part,
of things.
yeah.
Okay, no problem. Thank you.
Sure.
Cool. Maybe
There's one more question here.
maybe we can take it offline.
Okay, sure.
Oh, sure.
Yeah, looks like we're out of time. Thank you, everybody. Thanks for listening.
Thank you.